So in the previous lecture, we were starting to look into the effects of, not the effects, particularly we were trying to look into what happens if we increase the size of the device, right? So why did we want to increase the size of the device? Yeah, so what about R naught? Okay, so in order to increase the R naught, we had to increase the R naught is directly proportional to L. GDS is inversely proportional to L. So if we have to get a high output resistance, we wanted to increase the length. Why do we need high output resistance? Yeah, so essentially Y22 we want to be 0 or R naught we want to be infinity. So in other words, we want more gain. So we want high output resistance, and we saw that for the same current, in order to increase the output resistance, we needed to increase the length of the transistor. What was the effect if we only increase the length and don't do anything else? Keep the W same and increase the L. What is the effect of that? Current decreases, true, but in order to, so what is the side effect of that? Decrease of current. Yeah, biasing point gets affected. Which small signal parameters get affected? GM gets affected, GDS get affected, both, right? So let's assume we want GM to be same, because ultimately the gain is GM times some resistance, right? So if the resistance doesn't change, then the gain is proportional to GM. If the I changes, if the current reduces, GM reduces, which means my gain reduces, right? So ultimately we would want to keep the GM also to be same. So which means that in the configurations that we have used till now, we need to increase the W also. Essentially, we needed to keep the W over L constant, right? So now this is what we were discussing in the previous lecture, and this is where we stopped. So if we only concentrate on the incremental parameters, so this is what the incremental model will look like. Okay, but then we saw that this is probably not a accurate representation of what a transistor is, because we have neglected the effects of capacitances, right? And moment you increase the device size, we saw that the capacitances also increase proportionately. The CGS capacitance, for example, the capacitance that will come between the gate and the source, which in this case will be gate and ground because source is grounded. We'll have a capacitance here. We'll have a capacitance between drain and bulk is grounded. So we'll have a CDB here. And we'll also have a CGD here. And we said that we'll consider the effect of CGD later. We were trying to figure out what is the effect of the other two capacitance to start off, right? By the way, how does CDB scale if I increase both the W and the L? Let's say I increase both W and the L by a factor of 2. how much will CGS increase by and how much will CDB increase by? CGS, what is the root cause of the CGS? Overlap is one part, but that's not the main component, right? What is the main component? This is the gate capacitance. So area of the gate increases, the capacitance increases proportionately. It's proportional to the area of the gate. So if we increase both W and the L by factor of 2, CGS will go by factor of 4. What about CDB? Is it proportional to both W and L or proportional to only one? CDB was? It was proportional to the W, right? Because the length was in the channel, but this was the capacitance between the drain contact and the bulk, right? So if you don't recall, so the capacitance between this, whatever we call is the drain, and the body was the CDB, right? And that was proportional to the W of the transistor, not the length. Length was the channel, right? So in other words, if we increase both W and L by a factor of 2 or 4 or whatever, CGS increases much faster than CDB. Okay, that is something you should keep in mind. It might come in handy when you will be designing. Okay, fine. So now we wanted to discuss about what is the effect of, once we put all these capacitances together, how does the response change? And before we go to that, let me take a step back and have a brief refresher of what a pole means, right? Because ultimately, when we are writing transfer functions, we are writing transfer functions in terms of numerator over denominator, right, as a function of S. So in this case, let's say I have a first order transfer function. So this is the refresher. So let's say I have a first order transfer function, H of S, which is 1 over 1 plus S by P. Okay. So let me call this V naught over Vi, some V naught over some Vi. Okay. And if I tell you this is a real transfer function, this is a transfer function of a real system, what can you comment on P? Is this real or imaginary? Can it be imaginary or it has to be only real? It can be imaginary, not SP. Mathematically, it can be either, but in a real system. So, are you comfortable with this idea that the poles should be in a real system should be complex conjugate of each other? Signals and systems, right? So which means that sigma, let's say j omega, if one pole is here, the other pole should be here, right? But if you have only one pole and it has to be complex conjugate, then it has to be on the x-axis because the other one doesn't exist, right? So P has to be real for a first order system, which is a real system, right? So P has to be real. That's cool. And let's say this is the H of S, where this is V naught, Vi, and I give a step input. Now in time domain, so this was in S domain, I'm giving in time domain. This is VIT, which is step. What will be the output? Can you calculate and tell me? So the step input is 1 over S. So V naught S will be 1 over S times 1 plus S by P. So you do partial fraction. Right? So you do the inverse Laplace of this. So you get T times, this is ut. So P minus e to the power minus right? So some of you might be thinking that it's probably that the notations are inconsistent. So what I will do is I will, instead of making this 1 over, the dimensions will make it like a naught times. So this becomes a naught times some gain, right? So this becomes fine. So why is this important? This is important because so what does this remind you of, this guy? It's like a charging, discharging of a first order system, right? In this case, it's like a charging of a, almost like a capacitor of an RC30, right? So I mean, what is the key component of a charging that you are interested in when you look into, let's say, charging of a capacitor in a first order circuit? Time constant, right? And what is the time equivalent of time constant in this expression? 1 over T, right? So the time constant tau is 1 over P. So there is a direct relationship between the pole of a first order system and the time constant of it in the corresponding time constant in the time domain, right? So essentially, this means that poles relates to tau. Okay. And since we took a generic first order system, that is generally true. Okay. But only true for a first order system. Okay. Okay. So again, why is this important? This is important because it gives us a quick and easy handle of analyzing what the equivalent time domain response will be by looking into the frequency response of the system, right? So what will be V naught S over Vi here? Say I do mod. So what should I get if I plot this guy? Not this guy, sorry. If I plot the transfer function, which is this guy. So I'm trying to plot a naught by mod of 1 plus S by P. Obviously, in this case, this is omega, because I have to replace S with j omega, right? So what will this be? What is mod of this when S equal to j omega? Let me replace this with j omega also. What should I get? Yeah. So, and what will be the expression of this? And what will be the angle? Right? So if I have to plot the magnitude transfer function first, so what should look like? What should this guy look like? This should, at 0, omega equal to 0, this should be a naught, right? So this should be a naught. And at omega equal to infinity, it should go to 0. And this should be like something like, what is happening here? Let me restart the system once. So yeah, so this guy will start from DC and go to 0 at omega equal to infinity. But I mean, we essentially to some extent cheat and say that this looks like a smooth curve from all the way from 0 to infinity and with different slope at different points in the curve. So what Bode told us is that you don't have to do anything, all these things. The first simpler way to do an engineering approximation is to figure out if we can express this plot as a straight line segments, right? So in this case, what we will essentially do is say that looks like it is flat for certain period, certain range of omega, and then it is dipping down with a certain range of omega. And I mean, what we notice is that if we take a log of this, if we take a log plot of this, what will happen is we'll have some, it will be flat for some portion of omega, and it will also come down, right? It will eventually come down and go to minus infinity, right? And what will be the slope of this guy? Minus 20 dB per decade, right? So what Bode told us is this again looks to be too complicated. We'll make our life easy, and the way we'll make our life easy is the wherever it's seemingly flat, we'll assume to be perfectly flat, and we'll choose a point, an inflection point, where we'll say that it has started to roll off at minus 20 dB per decade. So essentially what we'll do is say that this is flat till some point, and then goes down at minus 20 dB per decade. And the choice of this flatness is obviously people have to agree. So what we tended to agree is we'll choose a point where the red curve is 3 dB below its DC point, right? So essentially this point is 3 dB. 3 dB below it from wherever it started. And this we call as the 3 dB bandwidth of the system, or omega 3 dB. Okay. And this is as far as the magnitude response is concerned, but we'll also have a phase response. If we plot the phase, so what should the phase look like? What should it start from? It should start from 0, tan inverse of 0, 0. And then it will go negative or positive? It will go negative, great. And what will happen exactly at omega 3 dB? By the way, I mean, since we have written this expression, what is omega 3 dB? P, right? So omega 3 dB in this case is actually equal to P. So what will happen at omega equal to P? What will be the phase? Minus 45 degree, because it's minus tan inverse of unity. So this goes to minus pi by 4. So it will go something like this. And then it will keep going down, and it will keep on going down, and it will settle to something. Yeah, it will settle to minus pi by 2. Okay. So there happens to be an approximation for this also, a piecewise linear approximation. What we tend to say is that this guy is also kind of flat here and flat there, and we'll extrapolate a straight. We basically connect these two flat lines with a straight line. However, in this case, because of the nature of the roll-off of the phase, we have to keep some margin, and the margin typically is 10x from either side. Right? So this essentially becomes 10p, and this becomes p by 10. Okay. And by the way, one thing I missed, when we are doing these plots, these are log plots, which means x-axis is now is also in log domain, right? So x-axis is this should be in log domain. By log domain, I mean for every equal increments, you go by a factor of 10. So if this is, let's say, 10 hertz, this will be 100, this will be 1000 or 1k, and so on. Okay. Okay, fine. So that's why, I mean, 10x on either side take up the same amount of space on a graph paper or a screen in this case. Fine. So this is as far as a first order system is concerned. So why are we spending so much time on this? We are spending so much time on this because you will see that we'll try to break our systems, whatever systems we have, into bunch of first order systems, because it's easy to analyze. And also we saw that the time domain response of a first order system corresponds to a what? It's like it corresponds to a typical RC charging, right? And we are comfortable with that. So since we are comfortable with that, we'll go back to our comfort zone. So so every time we write something in terms of a first order system, need not be a context of an RC circuit. It can be anything. At the back of your mind, you should think that the way this system will settle will be similar to how an RC circuit settles. Okay. One more piece of information before we move on is, can you comment on what happens to a system if tau is very large in terms of speed of the system? It's slow, right? It becomes sluggish. So since tau corresponds to 1 over p, if p becomes very small, your system will become sluggish, right? So essentially, that's why this omega 3 dB is also called the bandwidth of a first order system, right? So if the bandwidth of the system reduces, your systems become slower, right? It's equivalent to a very slow charging of a RC circuit. And if your bandwidth of the system becomes large, which means the time constant has reduced, which means your system will respond faster. Okay, so that correlation which we'll do time and again, without making it explicit every time. So a high frequency pole corresponds to a fast system. For high frequency 3 dB frequency, high frequency 3 dB bandwidth corresponds to a faster system, and low 3 dB bandwidth corresponds to a slower system. Okay, and we also know now how to relate the amount of fastness or the slowness, right? Because pole corresponds to tau. Okay, fine. So let's move on now. So the reason we are doing all these things is because we have a system which is certainly not a first order system. This we discussed in the previous lecture. This was R1 parallel R2. This is CGS. This is C1. This is second order system. But can we comment on, even before going into analyzing anything, can we comment on the purpose of, the relative sizes of C1 and CGS? Note that CGS is not totally in your control. You can size the device to some extent to increase or decrease CGS, but C1 is totally in your control. C1 is not a device capacitance. It's a capacitance that you have put to ensure that the signal goes through. right? So can you comment on the value of C1 with respect to the value of CGS? What would you want it to be? C1 has to be much smaller than CGS or other way around? C1 should be smaller.
RC1.
We'll get to RC, but tentatively, intuitively, what do you think? Ideally C1 should be what? 0 or infinity? It should be infinity. Now, infinity is not possible, so we figured out an upper limit. But ideally, in this case, C1 should be as large as possible. And CGS should be ideally what? 0 or infinity? CGS should be 0, ideally, because we don't want any attenuation of the signal at VG, right? So if we had, let's say, I mean, this is a I'll make an approximation, then we'll show why the approximation is valid later on. But let's assume that CGS were not there, right? Let's assume CGS were not there. Then what would have been the frequency response of this guy? What would have been the Bode plot equivalent of this guy? Not really. So what is the what is VG over VI? I should use a proper notation. So this is a high pass, low pass, band pass. What type of response? VG over VI? It's a high pass, right? At DC, clearly no signal is flowing through. At DC, your VG is 0 because capacitor is blocking away everything. At infinite frequency, C1 is shorted, and you get the maximum that you could have got in the, I mean, if in place of C1 had it been a short circuit. Correct? So this would start from 0. If you plot in log domain, this should start from minus infinity and then go and settle to some value, which is corresponding to 20 log of R1 parallel R2 by RS plus R1 parallel R2. Right? So I'll remove this 20 log part because it is implicit. Instead of putting in log domain, we'll assume that this is what it is. And obviously it will break somewhere, this guy. And in Bode approximation, what will this breakpoint be? Right. It will be 1 over time constant. Great. So what is the time constant? RS plus R1 parallel R2 times C1. Right? Okay. And so what will be the, I mean, if we just stare at this expression, at this plot, what will be VG over VI? I can obviously write out the maths, but if I just stare at this plot, what do you think VG over VI will look like? VG over VI should look like, it should have a 0 at DC, right? Do you agree with the fact that there should be a 0 at DC? Okay. So we'll have something at S. S times something, what that something is, we'll figure out later. But we should also have one pole because ultimately because of the pole, it flattened out, right? Otherwise, this guy would have increased at 20 dB per decade all through. So we have one pole, right? Now, what should I put in the bracket, in the parenthesis here? The DC gain is what? 0, right? So I'm curious, why did you say DC gain? There is a reason you said DC gain. Because if we put S equal to 0, we are supposed to get something, right? That's why I presume you said DC gain. But if I put S equal to 0, everything goes to 0. So that's not helpful. But can I put S equal to something? Yeah. So if I put S equal to infinity, what should I get? If I get S equal to infinity, I should get this guy. right? Because that's the gain at infinite frequency, according to high pass filter. So if I put S equal to infinity, what if I call this, let's say A naught, what should A naught be? So Vg over it will be A naught times P, which is equal to, from the plot, is R1 parallel R2 by so P we know, so we know A naught, right? What to put in the bracket. Okay. So the reason I am spending time on this is because you'll see that this will be helpful when we have multiple transfer functions putting together, and we would like to figure out what the coefficients are by looking at the plots instead of writing out the full-blown equations. Okay. So this is the expected high pass response if CGS were 0. But now let's assume the other condition, that at relatively high frequencies where C1 is supposed to act as a short circuit, right? Ultimately, the whole goal of putting C1 was to block the DC and pass everything else, right? That's why we had put C1. So if that is achievable, let's assume we have designed in such a way that the C1 can be assumed as a short circuit and only blocks DC and passes everything else, which means that at non-DC frequencies or relatively high frequencies or signal frequencies, however you might want to characterize this, this should look like, instead of C1, I'll have a short circuit. Then I'll have R1 parallel R2. And now let's see what's the effect of CGS. Right, so this is at non-DC frequency, let's say. Right? So this is again, an assumption has gone in. This is not mathematically accurate. This is an assumption that we have made. The assumption is at the signal frequencies, we are assuming that C1 is shorted. We are trying to break the second order circuit into equivalent first order circuits and see if it makes sense. Okay. So let's assume this is what it is. Then what will be Vg over Vi? What should Vg over Vi plot look like? What should it look like? Should look like a low pass. Something like this. What should be the cutoff frequency or 3 dB frequency of this guy? 1 over time constant. What is the time constant? So RS parallel R1 parallel R2, right? And what will be this, the DC gain or the gain of the flat portion? Right? So now if I zoom out of it, and I try to combine the effects of both of these plots, right? Again, not mathematically true, but if I want to combine the effects of both the high pass and the low pass, right, by putting things together, what should it look like? It should look like something like a band pass, right? And so what we are postulating is that this is again a postulate because we haven't rigorously proved it by mathematics. This should look like something like this. What should be the first frequency? First cutoff frequency? This should be corresponding to this guy, which is equivalent to the pole associated with the capacitance C1 when CGS was 0. Right? It's a pole associated with C1 when CGS were 0. So, and that would have been 1 over, I mean, that becomes pretty straightforward. That is 1 over Rs plus R1 parallel R2 times C1. And the second pole, right? The second pole will be equivalent to the time constant of the system when in the presence of CGS, but when C1 was what? 0 or infinite? Infinite, right? So if C1 had it been infinite, so it becomes shorted. So this becomes 1 over Rs parallel R1 parallel times CGS. And the gain here is whatever we saw, right? So this gain was R1 parallel R2 by Rs plus R1 parallel R2. So this is what we expect it to be, right? So this is what we expect the VG over Vi to be. Okay. So a quick sanity check. Should it make sense? If among C1 and CGS, when you put non-infinite values, like real values, what would you like to you would expect C1 to be much higher or CGS to be much higher? C1 to be much higher, which means the pole associated with C1 should be much lower. I mean, granted that I kind of hand waved the resistive part, but let's assume that still, I mean, R1 parallel R2 is also in your control, right? R1 and R2 is in your control, C1 is in your control. So it's possible to ensure that this pole is as much towards the left-hand side or towards the origin as possible, right? So your choice of signal frequency, right? Your choice of signal frequency or your choice of R1 and C1 should be such that the signal frequency falls within this band, right? If the signal, if I tell you that design something for 1 kilohertz, right? You have to pass 1 kilohertz unattenuated. So you have to ensure that this lower cutoff frequency is lesser than 1 kilohertz and the higher cutoff frequency is higher than 1 kilohertz. You cannot use probably cannot use the same circuit if I tell you now design something for 100 megahertz. Then you have to see what will be the higher cutoff frequency. Then you have to probably size your R1 parallel R2 and size your device so the CGS is not too high and so on, right? So these are design choices you have to make when you are designing anything. Okay, fine. This is as far as working with intuition is concerned, but I mean, whenever we use intuition, we have to also validate it and see that whether we are going wrong somewhere, right? So what we'll do, we'll use the brute force mathematics to go ahead and see whether whatever we have been talking about makes any sense or not. So can you tell me, looking at your previous notes, what will be VG over Vi in S domain, the full-blown second order? So instead of R1 parallel R2, let's call it R12. I mean, otherwise the algebra becomes clunky. So there will be some S squared times something. What will that be? You can look at your notes until. Yeah, right. So C1 CGS. In this case, R1 to Rs. Then something S times R1 to CGS. Rs C1. Okay, plus 1. This I remember. What is the numerator? S times C1 R1. Okay, fine. So we'll have to make sense of this. I mean, second order equation, obviously one can find out the roots to find out the poles, but again, becomes messy, right? So what we'll try to do is to use some approximations. The approximations that we will be using are as follows. That we know a priori that what our expectation is. Our expectation is the two poles should be far apart. which means the roots of the two equations, two roots of the equation should be far apart. They are not of the same order, right? So when you have a quadratic equation, so firstly, let me express this as this in this form. Okay. So I should express in the minus form, because when we find roots, it will become, it's expected that it is 1 minus, right? Or s minus something, that becomes a root. Otherwise, I mean, poles might appear to be in the right half plane. So essentially, what I'm trying to point out here is that we know that from, so if I have to essentially factorize this and find out what P1 and P2 are, so one way to go about doing is finding out the factors using brute force minus b plus minus square root of b square minus 4ac by 2a. But that becomes mathematically, as you can see, symbolically involved, right? So what we will do, we will use one method of factorization, and that is, if we know a priori that the roots of this guy are far apart, then we will use the properties of the roots, right? One property is P1 plus P2 is sum of the roots is minus b by a, and the product of the roots is c by b. C by a, right? C by a, sorry. Right? So if we know a priori that P1 and P2 are far apart, which means there is a dominant pole. Right? So if let's assume that if P2 is much greater than P1, then I can simply say that P2 is equal to minus b by a. And then I plug in that value of P2 in the other equation, I should be getting minus c by b. Right? So why am I doing this? Because at least I don't have to factorize using those big terms. I know which is a, b, c in this equation, and I'll just simply plug in those values. Okay, so let's do that. So P2 will become minus and P1 will become minus c over b. Okay. Any questions? Any confusion? Did I make a mistake? I tend to sometimes. So keep me honest. Okay, so let's take the easier one, that is, looks like P1 doesn't have any numerator, so let's use P1. So P1, let's go to mod of P1, because ultimately we all know that the stable system poles are on the left hand side. So let's deal with mod. So this becomes 1 over, can I club some things? Let's club C1. C1 RS plus R12 plus CGS R12, right? So again, if I sketch the circuit here, this is RS, C1, R12, CGS. Assuming that we know that C1 will be much larger than CGS, this I can approximate as 1 over C1 times Rs plus R12. Right? Make sense? So does this correlate with anything that we got using some intuition? Where was this? Where was the plot? Okay. This guy. Right? So the one of the poles seems to be 1 over C1 times Rs plus R12. R12 is R1 parallel R2. Right? So this is possible as long as we honor this condition. As long as we honor that this guy is much greater than this guy. Right? So that is fine. What about P2? So let's see P2. C1 is dominant, right? So we'll club C1 together again. So this becomes C1 Rs plus R12 plus CGS R12. Let's break apart these two. So this becomes Rs plus R12. Right? So again, which of these two terms do you think is dominant, or is there a dominant term between these two? Note that C1 is much larger than CGS. First one, right? So this one will be much lesser, right? So since this is this, which means this becomes Rs plus R12 CGS Rs. So what I'll do, I'll just take Rs to R12 the denominator. The reason will be apparent right now. Okay. So what does this look like? Yeah, but this looks like an RC, where C is CGS. What is the equivalent R? Rs parallel R12. And what is R12? R1 parallel R2. Right? So again, if we sketch our so this was under the condition when we said that for time constants, input is not required, right? So we can as well get rid of that. So the time constant associated with CGS when C1 was infinity, right? So essentially the time constant associated with this network, right? So that would have been exactly what we got with the approximations, right? Make sense? Okay, fine. So which means whatever we did earlier was not too bad. Okay, so instead of, sometimes it will not be possible, you will see, to write out full-blown equations because it's only second order. If it becomes third order, then it becomes almost impossible to do any hand calculations. However, we'd like to get some intuitions under the assumptions that we know what the expected behavior of the network is. We can then ease our calculations and make the circuits bunch of first order circuits. Sometimes it's possible, sometimes it's not. Wherever it's possible, we'll have to go ahead and do it. Okay. Okay. So now questions? Oh. So again, for the sake of completion, so this we figured out is P1 or mod of P1. This is mod of P2. And this we know already what the gain is supposed to be. This is supposed to be R12 by Rs plus R12. Okay. So if I now look into this So let's assume I have this network now, and without writing out the full-blown equations, we have figured out this is what the response should look like. So what strategy will you use to figure out what the mathematical expression of this will be? By that, what I mean is, I know that this will be 1 plus S by P1. This is 1 plus S by P2, where P1 and P2 we figured out using time constants. I know there is a 0 at DC, but what will be this, let's say some A0? What will be this A0? How will you figure that out? Here, the only unknown till now is A0. I mean, I can always write out the equation and figure it out, right? But the whole purpose of going through these multiple steps is to show you that you don't have to write out the full-blown equations all the time. So you can look at this and plot this in 1 minute.
So we can break it into the position of low pass and high pass filters and then calibrate for the.
Yes, we can definitely do that, but then what will it come? What will it boil down to? Will be equal to what? You have to equate that to something with relates to A0, right?
Yeah.
So in case of low pass, we had put S equal to 0. So everything vanishes and we get that coefficient. In case of high pass, we put S equal to infinity. Everything vanishes, we get some coefficient. In this case, it's a band pass. So what value of S should you put? You have to put somewhere in between these two poles, right? Half or anything above P1 less than P2. That's what the Bode approximation is telling us. But if you put all those values, you will get, again, some clunky number. But we are not looking for a very clunky number. We are not looking for an accuracy of like 1% or 10%. It's okay if we get a ballpark range. So what does another thing of Bode approximation tells us? So let's say, let me take another detour. So let's say I have a plot like this. Okay. Again, let's say this is H of S, mod of H of S. I have a pole here, let's say at P1. I have a pole here, let's say at P2. Okay. So I express this in the form of A0 by 1 plus S by P1, 1 plus S by P2. And if I say that I am interested in finding out the equation of this guy, what will be H0 of S when omega is much less than P1? What will it be? H of S when omega is much less than P1. What will it be? It will be A0. And looking at this, what are you doing to get that? You are putting S equal to 0. You are not particularly concerned that S can be non-zero values also. Right? We are putting S equal to 0 because we are assuming we are operating at a frequency much lower than P1. Right? Okay, so now let's get to this guy, the last part of the plot. Right? So what will H of S be when omega is much greater than P2? You cannot put infinity. I want the equation in terms of S. Right. So basically, in both these cases, this S plus P1 and S plus P2 will dominate over 1 because we are operating at a frequency much higher than P1 and P2. Right. So essentially, this becomes A0 by S by P1 times S by P2, which means A0 P1 P2 by S squared. So now let's come back to the middle guy here. So what will this be? Which is much higher than P1 and much lower than P2. In case of Bode plot, it doesn't make a distinction of much higher and much lower. Just higher than P1 is equivalent to much higher than P1. Just below P2 is equivalent to much lower than P2. That's the Bode approximation. So using Bode approximation, what will H of S be in that middle segment? A naught by S by P1 times 1, because S is much less than P2 and much greater than P1, right? So for this section, S by P1 will dominate. For this section, 1 will dominate, right? So it becomes A naught by S by P1. That is why Bode approximation is so powerful, right? You don't have to deal with those smooth curves where you don't know which is dominating. In this case, straight line segments, you clearly know which is dominating. Yes.
In the above case,
We'll come coming to the above place only, because we want to solve this case. That's why I took the detour. So now let's solve this case. So where are we trying to measure? Yeah, we are trying to get the information somewhere between P1 and P2, right? So if we want to get the information of somewhere between P1 and P2, what will this curve look like, or what will Vg over Vi, the expression of the Vg over Vi will be? So let me write it out again. So Vg over Vi is S times A naught mod P2. So we want Vg over Vi for omega greater than P1, less than P2. Yes, so what should I do? Help me. Numerator will be? Yeah, S times A naught, and denominator will be?
S times P1 times 2.
Times 1. So this essentially becomes A naught times P1. And A naught times P1 is supposed to be R12 by Rs plus R12, right? So this becomes. So we essentially end up knowing all pieces of the puzzle. P1, P2, we came to know from time constants. We figured out what the transfer function should look like by looking at whether it will be high pass, low pass, or band pass. And the only other piece of the puzzle that was necessary was A naught. A naught we could figure out by plugging in Bode approximations and which part of the plot or frequency are we interested in. Okay, make sense? Okay, fine. So this is as far as the input side of the common source amplifier is concerned. So let me. So now let's switch focus to the output side, right? So incrementally, we figured out if this is Vi, this is Vg, what will be Vg? And we now figured out at what range of signal frequencies we should operate. And if we are not satisfied with that, we have to change the component values in order to ensure that Vg at least falls within that pass band range. Okay, so now let's switch focus here. And we have a CGD, or rather CDB, right? Okay. So incrementally, what should the output side of the network look like? Again, I mean, if I sketch the input side and if I sketch the entire network, this should look like the incremental equivalent is this. You have a GDS. Then there is an RD. Let me write in terms of RDS. Then you have RD. Then there is a CDB to ground. Then there is a capacitance C2. And then there is an RL. And we neglected the CGD for the time being. Okay. So if we are operating in that mid-band section, then we know that, and if we have sized RS and R12 appropriately, we know that GMVG is approximately equal to GMVI. Right? So we don't have to bother about this guy. This guy is kind of frequency independent if we are operating between P1 and P2, where P1 and P2 were the frequencies that we determined in the 5 minutes back. So what we are particularly now interested in is this. So if this is, let's say, GMVG, which is, let's say, I, some I in. So this becomes RDS parallel RD. We have CDB. This is C2. This is RL. We are interested in what the output voltage will be when the input current is GM times VG or I in, right? Okay. So now, again, do you think it's a first order circuit, second order circuit? Second order circuit, great. So we have 2 poles. That's for sure. Do you think this guy has a 0? Let's do the easy part. Let's see. Do you think this guy has a 0 at DC? It has, right? It doesn't pass DC. The definition of 0 is it doesn't pass that frequency, whatever the 0 is. So clearly it's not passing DC. So you'll have a pole, 0 at DC. So it has at least 1 0 in 2 poles. Okay. So if we so our V0 over I in, let me reverse the signs, otherwise I'll have to deal with negatives. We'll have 1 plus S by, it's a P3. 1 plus S by P4. And I'll have a 0 times some, let's say, A2. So first things first, what will be the unit of A2? Will it be unitless or will have some unit? Pardon? Why should it be unitless? Because what is the transfer function that we are looking at here? Is voltage by current. It should have a unit of, it should be ohms, right? Okay, fine. So that is a good sanity check to have. But let's concentrate on P3, P4 first, right? So let's assume again, we will do the same approximations that we did earlier. What do we expect? C2 is totally in your control because you are the designer, you have put that C2 in place, right? So what do you expect the C2 to be? Very high, very low? Very high, right? You expect C2 to be ideally infinity. And again, you expect ideally close to 0, right? So it again looks like it's possible to, it's a fair enough assumption to assume that the poles are far apart, right? If poles are far apart, we can make the approximations that we did, right? So let's do the approximation right away. So what will be P3? Let's say P3 is associated with C2. What will be the pole P3? So which means this will be some time constant, which is 1 over time constant. In the time constant, you have a capacitance terms and a resistance term. I'm trying to figure out the it's recording, it's saying. Okay, so the pole associated with C2 will be what? We assume CDB is 0. So the pole associated with C2 will be so this guy RDS parallel RD and then plus RL, right? Plus RL. Because while we are trying to find out time constant, we have to desensitize any independent sources. For this particular purposes, in the independent source is our current source. Setting current source to 0 is equivalent to opening it up. So this becomes P3, this becomes mod of P3. What will be mod of P4? This should correspond to the case where when C2 is infinite, right? So we are trying to figure out what is corresponding to the time constant associated with CDB when C2 tends to infinity. So it will be 1 over CDB times RL parallel rate, RL parallel RDS parallel RD. Okay, so simple. What about A2 now? What should A2 be? Or in order to figure out, I need to figure out what will be the mid-band gain of this system, right? So what will be the mid-band gain? By mid-band, I mean between P3 and P4. So again, if I sketch it, something like this. So this will be P3, this will be P4. I'm trying to figure out what this will be. So for that, I at least need to know what we expect, right? So this will be V0 over S, then V0 over I, when S is greater than P1 or omega is greater than P1 and less than P2. So this should be what? So let me put this back. So what did you expect V0 to be in mid-band? So in mid-band, what do you expect C2 and CDB to behave like? C2 should be shorted and CDB should be open, right? So C2 is shorted, CDB is open. What should V0 look like? I in times?
And A2 times P.
No. I mean, looking into the circuit in terms of the components. So this, yeah, right. So this is I in times RL parallel RDS parallel RD. Right? So all we have to do is to say that this is supposed to be GM minus GM times VG times RDS parallel RD parallel RL, which is supposed to be equal to A2 times P3, right? Because again, I use the Bode approximations in this, and I know P3, I know everything on the left-hand side, so I'll know what A2 will be. Okay, make sense? Okay, we'll stop here.